We want to begin our discussion on conservation of energy. We've already talked a little bit about potential energy, but now we want to look at how we're going to use potential energy and kinetic energy and conserve overall energy. So the way we're going to talk about conservation of energy is using energy bar graphs. And the idea behind conservation energy and the energy bar graphs is that energy is neither created nor destroyed. We're going to visually show that energy is neither created nor destroyed by using these energy bar graphs. So let's start off by dropping a rock off of a tall tower again. So here's my tower, and I'm up on top of the tower like I was before, and there's the rock, and the ground is down here. And we're going to start off by letting the ground level be my y=0 level. And the tower is going to have some initial height of y0. That's where the rock is going to be at the top of the tower. In that scenario then, we know that the potential energy due to gravity, I'm going to use the letter V for potential energy, so V due to gravity is equal to mg times y0, the initial y value. And if I'm dropping the rock, then the kinetic energy is equal to 0. And so the way my energy bar graphs are going to look is like this. I'm going to have a bar graph for kinetic energy and a bar graph for gravitational potential energy. Now in the initial scenario there is no kinetic energy, so the energy bar graph for the kinetic energy is 0. But the potential energy does exist, and so I'm going to give it 4 bars of value. And the number doesn't really matter, it's more for demonstration purposes. Then as the rock falls under the influence of gravity, that potential energy is going to be converted to kinetic energy. So if I were to look at what's going on right here at about the middle, then there is now some movement, so there's going to be some kinetic energy, and I'm not quite as high as I used to be, so there's going to be less potential energy. So less potential energy is pretty much going to be 2 bars, and that means that there must be 2 bars of kinetic energy. The idea here being that there are 4 bars total up here at the top. Since energy is neither created nor destroyed, there must be 4 bars down here at the halfway point. And then finally at the bottom, we know that the gravitational potential energy has gone to 0, and so it's all kinetic energy. This is before it's hit the ground, but just before it's hit the ground. So I must have 4 bars of kinetic energy down here at the bottom, because I'm conserving my energy. So that's what it looks like graphically. The equations would look something like this. Here at the top, I'm going to have 0 plus mg y0. In the middle, I'm going to have some 1/2 m v squared plus mg y0 over 2, because I'm halfway down. Now since energy is conserved, these two must be equal. So that means that mg y0 plus 0, so I don't show that, equals 1/2 m v squared plus mg y0 over 2. So there's the math that goes with the description. Here at the bottom, I have some kinetic energy, 1/2 mv final squared, plus no gravitational potential energy. So mg y0 equals this must also equal 1/2 m v final squared. So by conserving energy, these 3 equations, these 3 expressions, must be set equal to each other. So let's do this again. So there's my tower, standing at the top, dropping my rock. This is some distance y0 to the ground. But this time, let's let y=0 be here at the top. So in this scenario, I'm dropping the ball. It's going to fall under the influence of gravity. But when I drop it, it has no kinetic energy. So when I look at my energy bar graph, the kinetic energy is 0. But so is the potential energy, because I have set the system potential energy to be 0 here at the top. In other words, this is my datum here at the top. So as the ball falls, let's say here in the middle, then it's going to have some kinetic energy. And since it's the same ball, we're going to say it's 2 bars of kinetic energy. But I've got to have 0 bars total. So down here, and notice I'm below my starting point, so my potential energy is going to be negative. So down here I have negative 2 bars of gravitational potential energy. So my total is 0 bars, just like it was here at the top, with 0 bars here at the top. And then down here at the bottom, the kinetic energy is maximized, so 4 bars of kinetic energy. But I've got to have 0 bars total, so it must be negative 4 bars of gravitational potential energy. So negative 4 bars of gravitational potential energy. So 0 bars total. Well, if I look at my equation setup, I'm going to have 0, that's at the top, equals 1/2 mv squared minus mg y0 over 2. And that's going to equal 1/2 mv final squared minus mg y0. Well, if I look just at these outside expressions, 0 equals 1/2 mv final squared minus mg y0. That can be reduced then to 1/2 mv final squared equals mg y0 when I bring this term over to this side of the equal sign. But 1/2 mv final squared equals mg y0, that's the same as setting these two equal to each other. So the mathematics really does not change. In addition, I could take this term right here and bring it over there, and I would get the same thing if I took this term over here. I'd still get mg y0 over 2 equals 1/2 mv squared. I'll let you do that, but you'll see the expressions are identical. I should also point out, if I put the datum in here, I made that y equal to 0, still get all the exact same stuff. The mathematics would be identical. The bar graphs would look different, but the mathematics would be identical. So let's take a look at a vertical spring, and I'm going to start from equilibrium. So the spring looks something like this, and I'm going to put a mass on the end of it, m, and this is equilibrium, so I'm going to call that y equal to 0. The spring is fixed, say, to the ceiling. At this position, there's no kinetic energy, so I'm just going to start it from rest. So the kinetic energy is 0. In addition, I'm setting this equal to the datum, and so my gravitational potential energy is equal to 0. And I'm at equilibrium, so I'm going to add another term for spring potential energy, and that's also equal to 0, because it's in equilibrium. When I let go, gravity is going to pull this down. And so as I pull down, or as gravity pulls it down, it's going to have a certain amount of kinetic energy. I'll just give that 1 bar. Gravitational potential energy is negative, so I'm going to let that be 2 bars. Right? So that's negative. And then there's some spring potential energy, and I'm going to let that be 1 bar, V of the spring. And so the kinetic energy, positive 1 bar, the spring potential energy, positive 1 bar, gravitational potential energy, negative 2 bars. That's 0 bars total. And this arbitrary position here, I'll call it y1 for the sake of argument, that would be giving me an equation. So here at y equal to 0, I have 0 bars. And so it must be that 0 equals 1/2 mv1 squared, that's the velocity at this point, it's moving with some velocity, v1, minus mgy1, because it's negative, plus 1/2 k y1 squared. Notice kinetic energy, spring potential energy always must be positive. They can never be negative. Gravity can be negative. Because velocity is squared, kinetic energy must be positive. Because displacement, whether it's positive or negative, it's squared, and so the spring potential energy must also be positive at all times. There'll be another point a little bit farther down where the velocity is equal to 0. That's going to be the lowest point it reaches. If I look at my energy bar graph there, there's no kinetic energy. There must be more spring potential energy, and it must be farther down, and so more gravitational potential energy. But I still end up with 0 bars. And so I would find that this is equal to 0 minus mgy final, if you will, plus 1/2 ky final squared. And all of that's going to equal 0 because I'm conserving energy.